Oh my goodness. All right. So we have a cone, and we know the height of the cone is related to the radius by this. Can you tell that this is probably going to be like an important statement? Right? It's probably going to be something that we need. Find the rate at which the height of the cone increases when the height is 0.5 meters. So I actually need, so the height and the radius and the volume, they're all changing, right? When the sand drops, they all change? Say yes.
Yes.
All right. And they're actually all functions. They're all functions of time. Before I talk about the related rates, I need something that relates those functions. What relates the volume and the radius and the height of a cone? David?
Is it pi? Oh wait, hold on. Pi r8. Oh wait, no, wait. 2/3 pi r8.
One third pi
Hold on.
squared is h.
Yeah.
So it's a third pi r squared h. Okay? It's actually a cone, and I don't know if you visually agree or not. I don't know where that went. A cone, if you think about a cylinder, a cone has a third of the volume as that cylinder does. Okay? I think there are a lot of different proofs. I think there's this guy Cavalieri, and what he did was he sliced it, and he took the ratios of the areas, and he looked at how those areas change, and so he would see like what part wasn't shaded, and down here at the bottom, the area of the cylinder and the cone are the same, right? The area of that slice. Here at the top, the area of the cylinder has a big area. The area of the cone has just that little point. And I think that's the way he did it. I'm not sure. Okay, so 1/3 pi r squared h. That's the relationship between all of the functions. I'm a little freaked out. Come on. Why am I freaked out? Yeah, there's so many variables / functions. Okay, so we actually know this relationship, which we thought was going to be helpful. H is equal to 4/3 R. Now, Gesundheit? Gesundheit. We don't need to know it in this problem, but there are problems that I've seen where when you look at a cone, do you agree this is R and this is H? There's actually a special relationship between R and H, and if you know, like, for example, I'm going to make numbers up. Actually, hold on, I think I can think about this. The height of the pile, no, that's not going to work. Hold on. All right, that's not really going to work, but I'll try. If you know that, like, this piece is 4 when this piece is 3, that actually sets up a ratio from geometry, and these are similar triangles. Do you see the big triangle and the little triangle? And since they're both right triangles and they both share this vertex angle, do you remember the theorem that we used to prove these similar? Nope.
Angle side.
No. It's actually, you're doing too much. You're trying to prove them congruent, and all we need to do is prove them similar.
Oh, isn't it just angle, angle, angle?
All we need is 2, because if 2 angles are the same, then 3 are the same.
Oh, right.
So angle, angle is one of the ways you could prove triangles similar. So this actually says, right, like H is to R as 4 is to 3. The whole thing is to the whole thing as the piece is to the piece. You don't need this in this problem. This problem is really nice because they give it to us. They tell us what the ratio is. But you could see, like, I don't know, in other problems where it might be nice to see the similar triangles. Students don't like that the first time it happens. They're like, how are we supposed to know similar triangles? Now you know. All right, I have a question. If we do this, 1/3 pi r squared, and I plug in 4/3 r, and I'm going to do it a little fast. I'm going to do 4/9 pi r cubed. And then check out the bummer. You ready to be disappointed? dv dt, so far so good. 3 times 4/9 over pi, 4/3 pi r squared dr dt. Let's look at the information they give us to plug in. Sand falls in a hopper at this rate. All right, where do I plug 0.1 in for? Try again. If it helps, look at the units.
It's volume.
Volume. Cubic meters, right? That's how much sand falls in.
So isn't it dV dt?
Yeah, but I thought a lot of you said dr dt. Didn't a lot of you say dr dt? Okay, sorry. So we know what dv dt is. They tell us the height. They said find the rate at which the height increases when the height is 0.5.
So should you put r in terms of h and then?
Yeah, look at all that. We have everything in terms of the radius, but they're asking everything in terms of the height.
1.5.
Okay, well, Dan is saying, you know what? I can deal with that. All I need to do is say what they're really saying is what, Dan?
That h equals, that r equals 4/3, h divided by 4/3, or 3/4.
3/4 h. Oh, man. Go back and do that whole problem again. That's a bummer. All right, so let's get that out of the way. Oh, that didn't go out of the way. It is crazy. I said get out of the way. Now get out of the way. There you go. All right. Volume equals 1/3 pi 3/4 h squared times h. I'm going to have to do algebra. Okay. Julia? And since it's h squared times h, are you okay if I just write h cubed? So let's see. 3 goes with the 9, so I get 3 pi over 16 h cubed. Is that okay? All right, so you're ready to do everything we just did again? Why didn't I? You know what? No one's listening to me today. Actually, I'm talking to the computer. Okay, so let's take derivatives. Derivative of v? That's still dv dt. All right, what do we have over on this side? I think. Yeah, what do you want to say? All right, so power rule. So Julia's taking 3 pi times 3, and she's doing 9 pi 16ths times h prime. And I didn't say this before, but I'm going to say it now. You like doing Newtons. I think Leibniz notation for related rates is better. What did I say yesterday?
You said that it's just hard to get like it better.
Yeah, okay. I'm reminding you. Because you didn't do that on your problem up there, did you? No, you didn't. Okay. And you said h prime. All right, so I'm going to write dh dt. I think we're good now. Can't we just plug things in? 0.1, 9 pi. Did they tell us what the height is? 0.5. Are you all right if we just stop there? Is that okay? I mean, so at this point we just need to do some arithmetic. Did you see how we had courage for the deed? We tried putting the radius, and we had tenacity. We weren't afraid to go back when we messed up, and we did it over again. Is that okay? All right, good. Do you want to ask the question? Did that seem okay because it was sort of like the sphere, but it was just a little different? No?
I think we could have spent some time. We found the derivative with r squared times r prime. we could have just plugged in what we found for the R and skipped all that. Doing it all over again.
You could have. We actually, based on what the radius is, we know how the height and the radius are related. The problem, though, is, oh yeah, right, totally. We could have found out, what we would have found, though, is we would have found out what dr dt is, and this wants to know what the rate, that the height's changing, right? So we would have had to figure out how the radius, the rate of change of the radius is related to the rate of change of the height. But we could have done that because we know this relationship. So we actually know that r prime is equal to 3/4 h prime, dh dr. Yeah, right. Gosh, all right, hold on, so we know that dr dt is equal to 3/4 dh dt. So Drew's saying instead of doing everything over again, we could have found this and then plugged in and solved for that. You're right. David?
Are we going to have to know that, like, 4-to-3 ratio thing?
Well, no, so I was actually going to say, in this case, it was really nice because they told us it was in a 4-to-3 ratio, but not all cones have a 4-to-3 ratio.
Oh, really?
Yeah, that's why I was sort of going through trying to explain that, you know, the cone, and I picked the 4-to-3 in that example, maybe that was bad, but the important thing is that the height and the radius are always in the same ratio no matter where you look. So if I don't tell you it's in a 4-to-3 ratio or a 1-to-5 ratio, I'd have to give you some information. Like I'd have to say, oh, the height is 5 when the radius is 7. And that would tell you that the height and the radius are always in a ratio of 5-to-7. So like there might be a little bit of thought that has to go into finding out what this relationship is. Sometimes it'll be given, sometimes it won't. So that was a good question. All right. Let's take a look at the ladder, because I think the ladder introduces yet another mathematical relationship. And I don't think I'm going to be able to get the picture today, but if you remind me tomorrow, I'll give you the demonstration of it. So we have a ladder that's leaning against the wall. And the bottom is moving out and the top is moving down. And this is unbelievable to some people, but they actually move at different rates.
Isn't that like when you do CD, like the outside
It's sort of like it, but not exactly. Like it's definitely like they're moving at the same revolutions per minute. One's traveling a further distance. I don't know if the analogy holds totally true here. The idea is that right here, when the ladder drops a little bit at the top, it actually goes out a lot at the bottom. And when it falls down like this, when it drops, did I say that backwards? When it drops a little bit here, it goes out a lot. When it drops a lot here, it goes out a little bit. I think that's what I wanted to say. And there's actually only one point in this ladder's fall where it's falling down at exactly the same speed that it's falling out. Arnie's got it, right? So when the ladder is exactly at a 45-degree angle to the wall, it's falling down at exactly the same rate it's falling out. Otherwise, those rates are different, which is bizarre. And maybe I'll give you the demonstration. Let's do it. Let's show you. Let's see.
Oh, the game on this problem, I thought the walls were moving. I was like, how did I?
All right.
You can do that in Geometry Sketchpad.
Okay, so one can do it, but I'm not the one that's smart enough to do it in Geometry Sketchpad. Someone far more capable than I set up a very nice Geometry Sketchpad demonstration, which I think is with the Camtasia, with the screencast going on, it's going to take a while to open up. So let's set it up, and then we'll maybe look at the demo if it pops up. Okay, so let's see. We know that the base is moving away at the rate of 2 feet per second when it's 4 feet from the wall. And I need to find out how fast the top is moving away from the wall. So I need a relationship between, I don't know, can I call this x and this y? Do you agree that x is moving and y is moving? And do you agree that they're both related to one another? When x moves, y also moves? And do you agree that they're also both functions of time? As time passes, they both move? Okay, so I need some sort of relationship that ties the functions x and y together. And I don't know why this is here. Anything talking to you? Ian?
I'm going to say that the perimeter always has to be the same.
I don't think so. I actually think this triangle, I think when it's an isosceles right triangle, we probably have a big perimeter. I think maybe here the perimeter is actually getting smaller, because this side's getting longer by a little bit, and this side's getting it shorter by a lot. That'd just be my guess. You want to try something else? Call on someone. You got a couple people who want to try something else. I like it. Is the ladder's height changing? Length changing? No, it's not. So I actually have a relationship here, and I can now take the relationship ties together the functions. Please don't try to plug anything in yet, because we haven't related the rates. All we've done is related the functions. So let's see. I need to do some math that will relate the rates. Oh, good. Here we go. Maybe. Okay. So, it's going painfully slow. All right, so I want you to look. Y is changing very little, and X is changing a lot. This is sliding the ladder up. This is way too slow. I should have done this tomorrow. Here, look, the ladder's hardly changing at all as it slides down, but the bottom is moving out very fast. And then we should hopefully see that these rates of change are going to be about the same when it hits like a 45. Oh, gosh. Is this killing anyone else? We did miss it. We can. We could bring this back a little bit. Oh, we could bring this back a little bit. So they're almost equal here. And you should notice that as y decreases by 1, x, or 0.1, x changes by about 0.1. And now x is moving much faster than y is. Right? So they're actually moving at very different rates. And that's sort of what I wanted to show you. Okay, so back to this. The derivative of x squared. Don't forget, x is a function. The derivative of y squared? The derivative of 5 squared? Careful! Good. I thought someone was going to say 2 5 to the first. 0. So now we have a relationship that relates all of those rates. And now I have to see what I know. All right. I know that the base, the bottom, is moving away 2 feet per second. What is that? Is that dx dt? Is that how fast this is moving? Yeah, I think so. So I know that this is 2. What else do I know?
You know that x is 4 because the base is 4 feet from the wall.
Okay, so x is 4 because x is 4 feet from the wall. Do I know anything else?
You substitute in for y.
Tell me what you mean.
Well, can you get it with one variable since you know x equals y squared equals 5?
David's saying we know that this is true. So when, not always, but when x is 4, we know y has to be 3. 3, 4, 5.
Wait.
No, that's what you told me to do.
No, not that. Never mind.
So when x is 4, and only when x is 4, y is 3. So actually, David said we can go back to that equation to find out the relationship between x and y. I like it. So we plug in for 3, and we have dy dt. And now we can solve, let's see, 16. So 6 dy dt equals negative 16. So dy dt equals negative 16 over 6. Do me do me a favor. Tell me the units.
Meters per second.
Is it meters or feet? Okay, feet. And tell me why I'm happy that it's negative.
Going down.
Yeah, why it's dropping down. Awesome. Very well done. I don't know how I'm going to do that in 30 minutes because we have shorter classes in the afternoon. So you did a great job in 35. All right. Now remember, get there fast. You're going to have to move.